Hello everyone and welcome back to the channel. Today we're rediving deep into a crucial process in metallurgy that often gets overshadowed by its more famous sibling, hardening. I'm talking about tempering. Why is this second step so absolutely vital? Why can't we just harden a piece of steel and call it a day? Well, stick around because by the end of this video you'll understand why tempering is the unsung hero that gives steel its incredible strength and reliability. We've got 5 key points to cover, and trust me, you'll never look at a piece of tempered steel the same way again. Let's start with the most immediate and critical reason for tempering: reducing brittleness. Imagine you've just taken a piece of steel and quenched it. It's now incredibly hard, which sounds great, right? But this hardness comes at a steep price. The quenching process, that rapid cooling, traps the steel's internal structure in a highly stressed state called martensite. This structure is very hard, but it's also extremely brittle. Think of it like glass, hard but one sharp impact, and it can shatter into a million pieces. A hardened, untempered piece of steel is very much the same. It has a high risk of cracking or fracturing under even moderate stress or impact. This makes it practically useless for most real-world applications. You wouldn't want a knife blade that chips the first time you use it, or a car axle that shatters when you hit a pothole. Tempering is the essential remedy for this problem. By reheating the steel to a specific temperature below its critical point, we allow the trapped carbon atoms to move around and relieve those internal stresses. This process makes the steel significantly less brittle and less prone to sudden, catastrophic failure. So point number 1, and arguably the most important, is that tempering transforms a fragile, glass-like material into something far more durable. It's the first step in turning raw hardness into practical strength. Now that we've made our steel less likely to shatter, let's talk about our second key point: improving toughness. This might sound similar to reducing brittleness, but it's a distinct and crucial property. Toughness is a material's ability to absorb energy and deform without fracturing. Think about the difference between a ceramic plate and a sheet of metal. If you drop the plate, it shatters. That's brittle. If you hit the sheet of metal with a hammer, it will dent and bend, absorbing the energy of the blow. That's toughness. Tempering is what gives steel this incredible ability. As we heat the hardened steel, the brittle martensitic structure begins to transform. Fine precipitates of carbide start to form within a softer, more ductile matrix of ferrite. This new microstructure is a game changer. It can effectively stop cracks from propagating through the material. When a small crack starts to form under stress, it runs into these tougher, more flexible areas, and its energy is dissipated. This is what gives tempered steel its amazing impact resistance. It's why tools like hammers and axes can withstand repeated, forceful blows without breaking, and why structural components in buildings and bridges can handle dynamic loads and vibrations. So, while reducing brittleness is about preventing shattering, improving toughness is about actively absorbing energy. Tempering is the key that unlocks this essential property. Let's move on to our third point, which is a bit more subtle, but incredibly important for manufacturing and precision engineering: enhancing dimensional stability. When you rapidly cool steel during quenching, it doesn't just get hard. It also undergoes significant internal changes that create massive amounts of stress. These locked-in stresses are like a tightly coiled spring, waiting for a chance to release. If you were to take a piece of freshly quenched, untempered steel and start machining it, you'd be in for a nasty surprise. As you remove material, you unbalance those internal stresses. The piece could suddenly warp, bend, or twist, ruining your precise dimensions. Even if it survives machining, these stresses can cause the part to distort over time, or when it's subjected to temperature changes or vibrations in service. This is a nightmare for any application that requires tight tolerances, like engine components, gears, or precision molds. Tempering is the solution. The process of reheating the steel allows the atomic structure to relax and settle into a more stable, lower-energy state. This significantly reduces those internal stresses. The result is a piece of steel that is dimensionally stable. It won't change shape unexpectedly during machining or throughout its service life. This ensures that the final component will fit and function exactly as designed, maintaining its precision and integrity for the long haul. So, for anyone in manufacturing, tempering isn't just about performance. It's about predictability and quality control. This brings us to our fourth, and perhaps most skillful aspect of tempering, balancing hardness and ductility. So far, we've talked about hardness, brittleness, and toughness, but there's another property in this mix, ductility. Ductility is the ability of a material to be stretched or deformed without breaking. It's what allows us to draw a wire or bend a paperclip. In their raw states, hardness and ductility are often opposing properties. A very hard material is usually not very ductile, and a very ductile material is usually not very hard. The true magic of tempering lies in its ability to let us fine-tune the balance between these two properties. How? It's all in the temperature. The specific temperature to which you heat the steel during the tempering process directly controls the final properties. A low tempering temperature, say around 200 degrees Celsius, will relieve stress and add toughness while retaining a large amount of the original hardness. This is ideal for things like cutting tools or bearings that need to be extremely hard and wear-resistant. If you use a higher tempering temperature, maybe 500 or 600 degrees Celsius, you sacrifice some hardness, but you gain a significant amount of ductility and toughness. This is perfect for components like springs, shafts, or structural bolts that need to be able to flex and absorb a lot of energy without failing. By carefully selecting the tempering temperature, a metallurgist can dial in the perfect combination of hardness and ductility to meet the exact demands of a specific application. It's this precise control that makes steel such an incredibly versatile material. Finally, let's bring it all together with our fifth point: improving overall service performance and lifespan. When you combine the benefits we've discussed, reduced brittleness, increased toughness, dimensional stability, and a tailored balance of hardness and ductility, what you get is a component that is simply going to perform better and last longer. Proper tempering ensures that the steel can reliably withstand the working conditions it was designed for. Let's consider a few examples. For a gear and a transmission, tempering provides the wear resistance to keep the teeth from grinding down, but also the toughness to prevent those teeth from chipping off under high torque. For a suspension spring on a car, it provides the ability to flex millions of times without breaking, a property known as fatigue strength. Tempering significantly increases fatigue strength by relieving the internal stresses that can act as starting points for fatigue cracks. For a chisel, it gives a cutting edge that's hard enough to stay sharp, but tough enough not to shatter on impact. Ultimately, tempering is the final step that guarantees the reliability and longevity of a steel component. It transforms a piece of hardened steel from a laboratory curiosity into a robust, dependable workhorse. Without tempering, the vast majority of steel applications we rely on every day, from the tools in our garage to the infrastructure of our cities, simply would not be possible. It's the process that unlocks the full potential of steel. So, there you have it. The 5 crucial reasons why heat treatment tempering is absolutely non-negotiable. It's not just an optional extra step. It's the process that makes steel a safe, reliable, and incredibly versatile material. We reduce brittleness to prevent shattering, improve toughness to absorb impacts, ensure dimensional stability for precision, balance, hardness, and ductility for specific jobs, and ultimately enhance the overall service life and performance of the final product. The next time you pick up a quality tool or rely on a piece of machinery, take a moment to appreciate the hidden science of tempering that makes it all possible. Thank you so much for joining me today. I hope this gave you a new appreciation for this critical metallurgical process. If you found this video interesting or learned something new, please hit that like button. Consider subscribing to the channel for more deep dives into the world of materials and manufacturing. Don't forget to ring the notification bell so you won't miss our next video. If you have any questions or ideas for future topics, drop them in the comments below. Thanks again for watching, and we'll see you in the next one.